Yeah, so hopefully we recall that our average rate of change is that exactly that. It's the change in whatever we're measuring over how long it took. The change in the distance over how long it took to go that distance, or the change in the speed. So if we're just talking about functions, it's the change in y over change in x, which in turn is the gradient. So that's what my gradient is, it's my rate of change. So if we want to know an average rate of change, we just want to know the quantity, the measurement at the start, the measurement at the finish, and how long it took to make that change. So in here, we've got our function 2x squared, and we want to know the average rate of change over 3 to 4. So f of 3, if we pop that in there, is 9 times 2, which is 18. F of 4 is equal to 4 squared, which is 16 times 2, which is 32. And so my average rate of change is y2 minus y1 over x2 minus x1, which is equal to 14. So my average rate of change is 14. And now by using a suitable domain, find an estimate for the gradient of the curve at x equal to 3. So if I was to sketch 2x squared out here somewhere, we're saying that between 3 and 4, the line that joins those points is an okay approximate for the gradient from 3 to 4. So a better approximate is to take a point closer to x. So maybe something like, I don't know, 3.1, or even, 3.1 will do. So if we instead work out, all right, f of 3, well, we know what f of 3 is. We just work that out to be 18. And if I work out f of 3.1, well, on my calculator, 3.1 squared is 9.61. If I multiply that by 2, I get 19.22. So the average is equal to 19.22 minus 18 over, what's it, 3.1 minus 3. So it's 1.22 over 0.1, which is equal to 12.2. So that's a better approximate because, if the closer we are to our point, the better my approximation will be. So we can see that if we zoom in. And even if we do it quick from our knowledge, if y equals 2x squared, well then the derivative dy dx is 4x. And if I put x equal to 3, 4 times 3 is 12. So that's the exact, that's the instantaneous. So 12.2 is a pretty good approximate. All right, so the gradient of the curve at a point leads us to that first principles rule. Okay, where f dash of x is, that's just, remember, my y2 minus y1 over x2 minus x1, which is why f dash of x is the gradient. All right, so, and the limit as h approaches 0 just means, like we did up the top there, if you like, my h value, the difference between 13 and 14 was a unit of 1, wasn't a very good approximation. The distance between 3 and 3.1 was 0.1, so h was 0.1 in that case. Much better approximation. And if I take h equal to 0.001, I will get an even better approximation again. So the smaller my approximation, i.e. if h approaches, the smaller my step size, which means the limit as h approaches 0, the better my approximation will be. All right, in terms of just evaluating limits, in short, we just substitute 0 in for h. And the only times that becomes an issue is if it A leads to a 0 in the denominator, or we get 0 over 0. And that's when some simplification can take place. For example, in A, if I just substitute h equal to 0, the last two terms become 0. So I just get 2x squared. That's fine. If I put h equal to 0 here, I get 0 plus 0 over 0. Now, if I get 0 over 0 form, it means I could factorize or cancel something. So if I mess around a little bit with the top. I could h out as a factor and get 4x squared plus 3h over h. And now those h's cancel in top and bottom. So that's really equal to the limit as h approaches 0 of 4x squared plus 3h. Now if h is equal to 0, I get 4x squared. All right. Obviously, the limit as h approaches 0 of 5x. There is no h, so it doesn't matter what h value is, I get 5x. Similarly, if h is approaching 0 and the function is just 3, it's always 3. So we just get 3. All right. So the one you've really got to be just a little bit wary of is in here where you end up with that 0 over 0 form. It means that there's something that could probably factorise. Example 3, what has this got for us? Consider the function. Sketch the graph of this parabola showing all intercepts and coordinates of the turning point. All right, so let's get the axes drawn up. X-intercept at +1 and -2. Just trying to work out a scale here. What if we make that -2, which means that there is +1. Coordinates of the turning point. The turning point is halfway between the two. So what's that? That's going to be there at -0.5. And if I put x equal to a half, -1/2, I'll get f of x equals -1/2 plus 2 times 1 minus -1/2, which is 3 on 2 times 3 on 2, which is 9 on 4. Oops, sorry, that rule was causing that. So I'm sure we can get a 9 on 4 in there somewhere. So 9 on 4 is 2 and a bit, so that's all right. I can get about up there. If I put x equal to 0, y will equal 2 times 1, which is 2, so it's fairly tight. So we can sort of go, it's not bad. Something like that. It's pretty good. What do I want to say there? We're going to say -1/2, 9 on 4, 0.02, 0.10, -2, What else? Sketch the graph of the parabola showing all intercepts and the coordinates of the turning point. Done. If P is the point x f of x and Q is some other point where it's just x plus h f of x, find the gradient of the secant or the line joining those points. So I'm going to be working at -2. So what if I just pick another section? So what we're saying is x is the point there, and let's just say that's the point Q. So if that's the point P and that's the point Q, that line there, actually I should undo that. Let's get our rule in there. That line there is the secant, okay, or the line that's joining those 2 points. So the first coordinate was the point x f of x. The second coordinate was x plus h f of x plus h. Now the gradient of the line. So remember the gradient m is equal to y2 minus y1 over x2 minus x1, which is equal to f of x plus h minus f of x over x plus h minus x. So f of x plus h means I have to substitute x plus h into that equation. So it might get a bit messy here. So let's there's x plus h plus 2 times 1 minus x plus h. Yeah, so there's f of x. So I might just work them both out separately. There's f of x plus h. F of x is equal to, well, I might expand it. I think it's going to be easy if I expand it. So x times 1 is x minus x squared plus 2 minus 2x, which is equal to minus x squared, x minus x plus 2. So there's f of x. I'm going to come down here now. Probably haven't set that up too well. What's that first bracket become? It becomes x plus 2, x plus h plus 2. It's very messy, isn't it? X plus h plus 2 times 1 minus x minus h. There's no easy way to expand this. Equals. So just x, boom, boom, etc. So I've got x minus x squared minus xh plus h minus xh minus h squared, sorry about that, plus 2 minus 2x plus 2h equals, it's only 1x squared, negative x squared, I've got a minus 2xh, I've got an x minus 2x minus x, I've got h plus 2h is plus 3h, and a minus, oh yeah, what's that term there? H squared, I think. Interesting. See if we've got that right. So now let's just slide into all of that. So let's work out f of x plus h minus f of x. I have to come across here. So I've got minus x squared minus 2xh minus x plus 3h minus h squared, subtracting green f of x minus x squared minus x minus 2. Oh, I forgot it. Oh, there's a 2 there. There's a 2 there. So I've got a plus 2 over here. All over x plus h minus x, which is h. And of course, we've got the limit as h approaches 0 of all that. So I get equals 2, right. Now, if we've got this right, we should get a few things cancelled out here. Minus x squared minus a minus x squared cancels. Minus x minus x is plus x, it cancels. Plus 2 minus 2. Ooh, hang on. What do we got there? I've got a sign out. Plus 2 in green, blue is definitely right. What's my minus? f of x, what's happening here at f of x? That's a plus 2 as well. So it should be a plus 2 as well. Yeah. Oh, sorry, so that's a plus, boys, which means, in short, that plus 2 and that plus 2 cancel. So that leaves me with, the limit as h approaches 0 of, I've got a negative 2xh plus a 3h minus h squared all over h. And I've got a h in top and bottom, so the h's cancel. H cancels there, 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 and there, which leaves me the limit as h approaches 0 of negative 2x plus 3 minus h, which equals negative 2x plus 3. Now, it took a long time. Right, so that's the gradient of that green line joining those points. One hopes. Now I'm going to cheat just a smidgen here, boys, because I've been able to, well, as we know, if we go back over, there's my answer. I'm going to put that back. Actually, well, I'll put it back because I've got negative 2x plus 3. Now, I should know my actual answer because I know if I expand the bracket and I have down here, I get negative x squared minus x plus 2. And so I know the derivative I should get is negative 2x minus 1. So I've made a mistake. So let's go back and find the mistake. So the mistake is there's a positive 2h there, which 2 times, looks like a w, I know, but it's a 2 times negative h. Should be a negative 2h, which makes that a negative h there, which makes that a negative 1h, which makes that a negative 1, which is what we should get. Yeah, and that's the advantage of doing anything first principles. You know the answer that you should get. All right, now that we've managed to fix that, if P is the point negative 2, 0, determine the gradient of the tangent to the curve at the point P. So that's easy. It's not, well, it's easy for me. We're saying that x is equal to, what happened there? Bring that back. We're saying that x is equal to negative 2. Yeah? So I've got a rule here that says the limit as h approaches 0 of f dash of x of, well, actually not f dash of x, of f of x plus h minus f of x over x plus h minus h is given by negative 2x minus 1. Therefore, at x equal to negative 2, the limit is equal to negative 2 times negative 2 minus 1, which is 4 minus 1, which is 3, which seems reasonable. It's a positive gradient. And if I do a tangent line there, it's going to be rather steep. All right. Now, you could go through the whole process again and pick the point 2, pick another point just marginally bigger or smaller than it, and go through the whole thing. But there's no need. We've got a general rule, which is what that first equation that we got was. Okay. And so, you know, that limit definition gives me the general rule for the derivative anyway.